We're now going to turn our attention to document databases, and we're going to use as our example the database called MongoDB, which is kind of the most popular and most well-known of the document databases. Just by way of introduction, you should also know that document databases are also referred to as NoSQL databases. So here's just some stupid resume humor. All right, so what are we talking about when we're talking about a document database? So first of all, MongoDB is such a database and it doesn't have any tables. You remember that I tried to really beat into you the notion that in a relational database, it's tables all the way down. Even a single scalar value, or what looks like a scalar value, is just a table with one cell. In a document database, it's documents all the way down. And document is a very generic sounding term, and of course, as usual, we're co-opting a perfectly good English word to have a very specific meaning in this context. So when we talk about a document, it's kind of the fundamental thing that a document database stores, and it's really just sort of a nested structure that can contain arrays and objects, or lists and dictionaries, or however you prefer to think about that. Usually these databases, and in particular for Mongo, we're going to actually interact with it by storing and retrieving what amount to JSON documents. So any kind of a JSON structure you can imagine, a nested list of lists of objects of lists containing objects, or whatever, counts as a document in a Mongo database. So everything is stored essentially as a JSON document. Now that's not really true. Under the hood, the database actually converts that into something called a BSON object, which is a binary form of JSON. But from our perspective as users of the database or programmers interacting with the database, we don't really need to know that. You can just assume JSON. Well, the structure of a MongoDB database is hierarchical conceptually in a similar way to the way that a relational database is. So at the top level, we'll see that the generic term that we'll use is just database, and that is equivalent to a relational database. There isn't a lot of structure above that in the abstraction, so there's not like a schema or catalog or whatever, just the databases. Databases contain collections of documents. So collections are kind of the moral equivalent of relational tables. They store multiple rows, and in the relational database, but in the document database, they store multiple documents. And then the document is really where the data live. It corresponds to the rows in a table. That's where the actual values are going to go for a particular instance of that table's structure. And in our case here, we're going to refer to those as the documents. And then those things are really kind of JSON objects, right? So the documents consist of these kinds of arbitrarily complex nested structures of JSON. So the attributes in a way are also themselves JSON objects. So it's kind of a self-referential thing, but that gives us a lot of flexibility. There is no structured schema. Now, that means that basically we can put any kind of document we want in the database. So any arbitrary structure of JSON can be stored as a document in a collection. And in fact, the default behavior for MongoDB and most other document databases is that you can actually store any shape of document in any collection. So although that, as you might imagine, might not be the best software engineering practice to have just a random arbitrary collection of things floating around inside of the database, it's possible to do that. Now that's usually touted as something that's a positive thing about a document database. It's very flexible, it's very agile. If you want to start storing new types of things in the database, you just start storing those things. You just change the shape of the JSON that you're inserting into a collection. You don't have to go and monkey with a schema and regenerate everything and figure out what to do with fields that don't have values but are required to have them and so forth. So very flexible. And my experience with these types of databases is that that's true. Particularly during development and prototyping and that kind of stuff, you can just store whatever you want in the database and it's there. Now, it also leaves me with a certain sense of unease about the structure of my data. So it feels, although it's flexible, it also feels a little bit dangerous in the sense that you don't have any kind of guarantees that you're kind of used to when you come from the relational database world into document databases. that are going to help you ensure the structure and content of the data that's in the database is correct. So you don't really have notions of referential integrity. You don't really have notions of a specific set of values that can go into each of the rows of the data, or in this case the documents in the data, and that just sort of feels a little bit like you're working without a net. One of the upshots of that is that you'll find that there's a greater tendency to denormalize data in a document database, because there isn't the explicit notion of a foreign key relationship as such. The tendency is to duplicate some data to make it perform better, to circumvent some of the issues around not having that kind of a relationship structure that's directly supported by the database. So that also kind of creates a kind of a sense of unease over the use of these types of databases. And I don't mean to prejudice you against them right from the get-go, but it is a very different paradigm than what we're used to from the relational database, where we have this kind of very sound mathematical formal footing, the relational algebra, that underlies everything that takes place in a relational database. Here, the design choices are made much more based on kind of practicality of being able to store flexible information in a database that scales well, as we'll discuss, and less of a focus on the formalities under the hood. That said, there's still a fair bit of information that we can make use of from our experience in the relational databases. So the notion of sort of one-to-many or many-to-many, right, this idea of the cardinality of relationships between the things that make up the data we're trying to store in our application, are universal. They're not specific to a particular type of database management system. We've learned how to store one-to-many and many-to-many kinds of relationships in a relational database, but that's not, again, specific to the relational model. In the real world, the entities that populate the domains that we're writing applications for are themselves found in relationships like these. And it turns out that we can leverage the same kind of data analysis and requirements gathering discussions that we have with our end users or customers and map that into structures that are present in our document database, just like we can do that in a relational database. So these aren't explicitly supported by Mongo, but you could argue that they're not really explicitly supported by a relational database either, right? We're kind of bringing to the table our idea of, say, a one-to-many relationship. And oh, by the way we implement that in a relational database is a foreign key from one table to another. So it isn't any more or less supported by either of these models. Still helpful to have that idea of cardinality and so forth in mind. We'll see that the query language for a database like this is very different from what we're used to with SQL. And as I mentioned before, these are sometimes called NoSQL languages. So there isn't really a structured query language for querying a document database. In fact, the queries, as we'll see, take the form of JSON documents. So you give it a piece of JSON that says, here's what information I want to get out from the database, and then the Mongo goes ahead and fishes that information up for you. There is support for indices. So the indexes that we've encountered in the relational model, used for performance and used to ensure some data integrity when you use a unique index, are also present in the Mongo model. So we can use those for performance. We can also use them for integrity, just like we did in the relational model, and create them and drop them and so forth, as we are used to being able to do in the relational database. One of the key reasons behind Mongo and the similar document databases was a desire to be able to have larger databases that perform more rapidly, particularly in the internet age, right? As websites required the capability to produce faster results, more results in the same unit time, to be able to store vast amounts of information at internet scale, the relational databases started to get a little bit creaky. And let's think about that a little bit in more detail. When we think about scaling to larger and larger databases, when we're thinking in the relational model, they're really designed principally to be kind of one coherent system that is easiest to implement on a single computer. It might have multiple cores and multi-threading and that kind of stuff, but really you're not going to partition that relational database out across 100 or 1,000 servers very easily. It's possible, and there's been more work on that in recent years, but historically that has not been the case. So if you wanted to scale your relational database, you did what was called vertical scalability. You're scaling up. The idea is that you're going to go buy a bigger, faster mainframe or a bigger, faster server that's going to run that database and have more disk capacity and faster speed and more processing cores and that kind of stuff. That kind of retains the monolithic nature of a relational database management system, but still allows you to grow over time. Now, a challenge with that is that eventually you're going to get to the biggest computer you can buy or the biggest computer you can afford. And after that point, you're going to have a hard time scaling to larger and larger systems because there just aren't any that are going to be any faster. The other approach to scaling is called horizontal scalability. So instead of scaling up in a single machine, you're sort of scaling out by adding a bunch of nodes to help distribute the load. Now, if you think about that process in the context of a relational database, it becomes evident why that's such a challenge. So, for example, even if you just had one large table of customers or something like that, and you wanted to distribute that table across multiple servers, you'd have to answer questions like, when I run a query, where do the data live? Do I have to send that same query to all of the nodes because they each have a subset of that table? Do I have to send them to one node and then have it refer to the other nodes? I mean, there's a bunch of different ways you could slice and dice that. But the relational model makes the assumption that you have this kind of monolithic table, this one giant relation that has these tuples in it. The document database, on the other hand, kind of embraces this notion of horizontal scalability. It's kind of built from the ground up to be able to scale out, to be able to just add more servers, and that gives you more capacity, more speed, more storage, and an ability to sort of balance the load across all of those servers. So again, it's really there to kind of support the scalability necessities of running applications on internet scale. You just buy more servers. And in fact, in most cases, these servers are really quite modest, right? They're sort of off-the-shelf commercial systems that are easy to buy, easy to install, easy to replace when they break. So you're not faced with this challenge of having to go to the very largest computer you can afford. You just buy a bunch of smaller computers and distribute the data across those smaller machines. So scaling out is a key aspect of the document database. MongoDB scales horizontally, as I've said, and it's, again, purpose-built, really, for internet-scale server applications. Mongo comes with a variety of command line tools. There's a program actually just called Mongo that we'll see how we use that, and it's essentially just a kind of a JavaScript shell that's got some additional commands wrapped around it. And there's a bunch of different utilities that come with Mongo that we'll touch on a little bit throughout this portion of the course. There is an astonishing number of programming languages that are supported by Mongo. So this is just a list of the official languages that are supported as of the time I made this slide a couple of years ago. There's probably more now that are official support. And then there's a community support of a gajillion additional languages. So this is another positive thing about using a document database like Mongo is you can call it from pretty much any language. Mongo, as a company, started out life as a firm called 10gen in 2007, and they've had, for the entire history of their existence, kind of a hybrid open source model. So you can just download MongoDB as an open source program and build it and install it and run it yourself without any licensing fees, or you can pay them for commercial support. And I haven't looked at this recently, but they were planning to have an initial public stock offering a few years ago. It'd be interesting to follow up on that. Now let's take a look at the CRUD operations that are supported by a document database. This is, kind of the bread and butter again of data storage. So we spent quite a lot of time talking about the SQL data manipulation language, right? The select, insert, update, delete functions, and those same CRUD operations are going to be present in any data management mechanism, including Mongo. So here's a little example of kind of how we would interact with Mongo. And again, we're going to use this shell that I mentioned before that's just kind of a wrapper around JavaScript. And if you think about that a little bit, you can see that this is a convenient language for interacting with a Mongo database because the Mongo database is storing basically JavaScript objects. So as I said before, there's many different languages that are supported by Mongo, but this one's kind of just a natural fit because It's fundamentally using JavaScript-like things under the hood. So we run that shell by just running the Mongo command at the command line, and it gives us some information about the server that it's talking to. And then this is an example of one of those kind of Mongo-specific commands that's been added. So use DVD rental. This switches, and then the database says, well, we've switched to the database called DVD rental. It's kind of an interesting approach that Mongo takes to these sorts of things. You'll notice that we didn't define a schema. We didn't have to do any, create table statements or create document statements or anything like that. We just said, hey, let's use this new database. And basically, Mongo brings that into existence from whole cloth on the fly. We mention it, and it starts existing as soon as we start putting data into it. The use command basically associates a specific database with this identifier db. So here in the next statement, we see db.actors.insert. So the db is the default name for the database. Remember that we have databases, which contain collections, which contain documents, which contain attributes. So db is the default name for the database that we have just told Mongo that we want to use. And then actors is the collection into which we want to insert some documents. And then the insert function is defined on collections, and it takes as an argument JSON information that's going to be encoded, well, in this case, JavaScript information, a JavaScript object here, that's going to be encoded as JSON and stored into the Mongo database. So we can see that in the same way that DVD rental database kind of sprung into life spontaneously when we mentioned it, the same thing is true of the collections within that. We didn't have to define what that collection looked like. We just mentioned it, db.actors, and as soon as we start using that thing, Mongo brings it into existence. So again, super easy, super flexible, not a lot of formality or formalism associated with putting something in one of these databases. And then the value that we're inserting, first name and last name, Penelope Guinness, I just took some values out of the DVD rental database that we've been using. And then the result that comes back says write result, and then n inserted says the number of things that were inserted. So we inserted one document in the actors database, in the actors collection of our DVD rental database. And you can see some additional examples here where we've inserted additional actors in the same way with just different values in the document. Now I can illustrate the use of some of the other methods that are defined on a collection. So db.actors.count gives us the number of documents currently in that collection. And then when I hit Control D, we bail out of the shell or bail out of the Mongo shell and head back to bash. So that's the create operation. Couldn't be simpler. Just start mentioning a collection, and put things into it. Now, when we want to retrieve information from the database, we can use another function, again, defined on the collection. So here's the actors collection, and there's a function called find. Now, we'll see that there is much more elaborate ways to query the database, but the default case is essentially select star from table. It's basically just giving us back all of the actors in this actors collection, and this is what comes back. And you can see here that we're getting back the information that we put in there, the first name and last name attributes of these JavaScript objects, but we're also getting this object ID. Now this is what Mongo uses as a unique identifier. So it fulfills very much the same purpose as a primary key in a relational table, but it's got to do kind of a bigger job in the sense that we want to have these object IDs not just be unique within a table, but to be globally unique across all the data in our database. And you can kind of start to see reasons for that. For example, if we're thinking about having a distributed database where the contents of a collection might be split up among a whole bunch of different servers as we scale out horizontally, we don't want to have any sort of central point of control that doles out those unique IDs. We'd like to be able to just kind of come up with them and have a guarantee that they're unique just by the way they spring into existence. So that object ID is something that's present in every object by that I mean every document in a Mongo database. So it's called, the attribute is called _ID, and it's essentially the primary key. It's a unique identifier for that particular document. There's kind of two ways of doing this. If you want to, you can actually supply that ID value explicitly. So back here, when we were adding information to the collection, we didn't give it one, so it cooked one up for us. So we can either supply it explicitly, or the object ID is created by the Mongo client. Now, that's what's the format here? Well, if we were to unpack those hexadecimal values here, we would see that the way that they work is that the first 4 bytes is a timestamp, and it uses, as in the case for most Unix kinds of timestamps, it uses the number of seconds that have transpired since the Unix epoch, which is midnight on January 1st, 1970. So it's just a count. It increments once every second, and that is what's used as in the first 4 bytes of the object ID. The next bytes, 4 through 6, are based on the machine ID. So this would be something derived from the host name or from the IP address or something like that, maybe a MAC address of a network interface. Then the next 2 bytes are based on the process ID of the client that's running, that's taking requests from the user to insert things into the database. And then the last few bytes are a sequence number that starts at, I don't know if it starts at 0 or 1, but it just increments each time you add something new. Now, something that may have been lost on you here, as I said, these are things that are done by the client. You notice that that's very different from what we're used to with regard to auto-incrementing synthetic keys in a relational database, where those are assigned by the server, right? We add a new row to a table that's got an auto-incrementing primary key, and the server figures out what's the next thing to assign to that in a very centralized kind of way. But when we're thinking about a distributed system here, where we've got a bunch of different servers running pieces of the database, we can't rely on a central server again for that purpose. Instead, the client itself is sort of empowered to generate these object IDs. And that's why the character or the contents of the ID has a lot to do with when it was created, where it was created, what process created it, and then a sequence numbering that's unique to that particular machine. The idea here is that by gathering together these 4 attributes, we're going to pretty much guarantee that any object that gets created anywhere in a distributed Mongo database is going to be globally unique, without any kind of coordination back and forth between the various clients that are accessing the database. And that's really important. All right, let's look at some additional ways of retrieving information from the document database. So here's the find command again, and in this first example, we're going to supply a kind of a pattern that we're going to try to look for. So rows, documents where there's a first name attribute where the value is alloc, and you can see that this just comes back with a single object from the database, a single document. We could also add multiple attributes to the find, and that's going to be more specific. It's going to basically do an and of those things. And we can see that that's the case if we look at this more verbose version of that kind of query. So in the second one here, we're just listing the 2 attributes that we're trying to query against. In the second or the third example, we're actually using this explicit $and we're giving it a list of 2 objects. And we're basically saying we want to have all of those documents that satisfy the first name being Rip and the last name being Crawford. Now this looks a little funny, that leading $, but that's actually just a weird kind of JavaScript identifier. Identifiers are perfectly legal to start with a $sign character. And the convention that Mongo observes, this isn't necessarily universal across JavaScript land, the convention that Mongo observes is that any of these kind of special keyword sorts of things are going to start with a $sign. And you can see in the next example here, we're doing a similar thing, except we're saying something as a disjunction. We're using or instead of and. So any document that contains a first name of Rip or a first name of Penelope should appear in the output. And that's what we see here in the 2 documents that are returned. The queries get a lot more sophisticated than this. There's a lot of other instances of these keywords and different things you can combine together. But this gives us a basic picture of how you would retrieve information from the database. It's not totally dissimilar to what we are used to in SQL. Basically what we're providing to the find method on the collection is the same kind of information that we would normally supply to a where clause. The first name is this and the last name is that. The first name is this or the first name is that, and so forth. So that takes care of the create and retrieve parts of the CRUD pattern. Let's take a look at the update part. Here's the first example of this is what's called the operator update, and it uses, again, one of these weird looking JavaScript identifiers. It starts with a $, and in this case it's set. So we're going to do db.actors.update, right? We had insert, we had find, and this is update. And we're going to have to give it basically two arguments. The first argument is the document that's going to be used to select those documents that are going to be updated. So in this case, we're supplying an object ID, which is going to result in choosing, hopefully, one unique document. And then the second argument is another document. Get used to thinking of like these JavaScript object thingies as documents. And that document is going to say, what do we want to do on the objects, in this case just one object, that satisfies the first argument. So we want to set a field called born and set that to 1964. Now notice that this is making a modification to the actors collection. And it's not making a modification to every document in that collection. We saw previously that we had inserted 4 things into that collection. Here we're only updating one of them, and we're updating it by adding a completely new attribute that isn't even present on the other documents. So this kind of goes back to what I was saying before, that we are kind of living in an all bets are off kind of a situation here. There's no guarantee that the contents of a document is structured in any particular way. Okay. And we can see the result that comes back here. It tells us how many things were matched and then how many things were modified. We'll come back and talk about upserted later. So if we go back and fish that document out again, same ID going on here, we'll see that we have a first name and a last name and now this born attribute. But again, that's the only document in the actors collection right now that has that particular attribute, the born attribute. That first type of update, what we call the operator update, that uses this set operator, is only going to replace a certain portion of the underlying document. There's also something called a replacement update, and these look kind of similar here until you notice that there's no $set going on here. We're basically saying, go find the document with this attribute, with this ID, and replace it in its entirety with this other document. So if we do that, we'll see here we've got one thing matched, one thing modified, and if we go and query that object again, we'll see that we have completely changed the contents of that particular object. And you'll notice that I'm actually working with the same document as I was up here. So previously this had first name, last name, and born, and now I've basically just clobbered the whole thing and replaced it with something new. Again, that might be super convenient, and it might be super confusing and lead to a lot of hard to detect bugs, but it's something that's supported by the update mechanisms within Mongo. And then finally, here's a way to delete values. So as you might expect, we're going to pass a document to this remove method of the actors collection that's going to identify a particular document within the collection. So that's a consistent pattern here for update and delete. Which one do you want to operate on? Same way that we use a where clause in SQL for this purpose. And it's going to tell us how many how many documents were removed. And now if we ask for the number of actors in our database, again, we see that it's gone from 4 down to 3. We can also use other types of selection criteria as the argument here. So here we're removing all of the documents containing a first name of RIP, and that is only going to match one of the current documents, and that's going to reduce the number of actors to 2. We can also, here's a really handy little function that we can use when we're accessing the data kind of ad hoc like this, is a pretty print operator. So we can say, we know that db.actors.find just returns all of the documents in that actors collection, but they're just sort of printed out in as compact a way as makes sense. And that's sometimes hard to read, particularly as the objects get more complex and have additional structure and nesting. So the .pretty method will print this out for us in a way that's easy for us to read. So same information, it's just broken out a little bit different. If we get bored of a particular collection, we can just get rid of it. So db.actors.drop is kind of the same thing as a drop table statement in the SQL data definition language. And once we've done that, we can see this other command that we haven't used before. We can say show, and there's some different things that we can show. And in this case, we're saying show us the collections. Well, because we had only accessed one collection in this extended example called actors, and then we had proceeded to go ahead and drop it, we can see here that we have no collections left in the database. Obviously, that's a very dangerous operation, and it's super easy to do. So again, don't have the usual backstop protections that the relational model offers us. So far we're using this kind of built-in Mongo shell, and as promised, there's a bunch of other languages that are supported by Mongo, so let's look at a couple. Here's the Python driver. We need to install a client called PyMongo that exports a class called Mongo Client, and then we can establish a connection to our Mongo server. I haven't really mentioned this, but of course this is a client-server architecture with a Mongo client running as a separate process, and we connect to it. The Mongo server running as a separate process, and we connect to it over different clients. So here's how we establish that connection. So we get a client object by connecting to a particular host name and a particular port. That's the well-known port for Mongo. We can get access to the different databases that are defined on that database. So here db equals client.dvdrental. I'm using the same identifier here as we did in the default case when interacting with a Mongo shell. But again, we're going to basically create those collections and documents within those collections on the fly by accessing them. Just to clean out any data that was left over from a previous run of this little example, I'm first of all dropping the actors table, which just eliminates it, and then I'm going to proceed to add some actors. And that's going to create the collection at the same time as the first one goes into the database. So here's those same 4 actors. I've just collected them into a Python list here, Python array, and then I'm going to iterate that over that array, and I'm going to call the insert command. There's a little bit of difference here between some of these language drivers and the way that the underlying Mongo JavaScript style client works. In particular, we have a function here called insert1, and then we pass it an actor, and then we ask for the value of the object ID that was created for that newly inserted actor. In the case of the JavaScript shell, it just kind of gave us that information for free when we did the find, but in this case, we can also ask for it as we're inserting it. So the actor ID is going to get stored here, and then I'm going to print out the details, the actor ID, the first and last name of the actor. I'm kind of using the old school Python formatting command here, but be that as it may. And then we're going to go back and query the database and fish out the actors one at a time, using the find again, no arguments, so we're not giving it a document that tells us which, we're not giving it a document that selects particular documents from the collection, and then I'm just using the standard Python pretty print to print out the actor. And here's what the output looks like. The first loop here, going over the actors during insert, shows us what we inserted there. So here's our first name and last name, and this is the object ID that came back from this inserted underbar ID property. And then the remaining lines are just a pretty printed version of a Python dictionary now that mimics what we saw previously coming back from the Mongo client. We can also access a Mongo database from a Node application. So this is a JavaScript program, but different from the built-in MongoDB JavaScript client. So same idea here. We're going to have to install a Node module called MongoDB. We can require that and grab the Mongo client object from it, or class. That gives us the access to the underlying connection. We're going to specify what we want to connect to, and a little bit differently here. This is just using a URL with a MongoDB type, and then we give it the host name and the port number, and then the name of the database that we want to access. Here again, I'm defining an array of objects that are going to contain the things we're going to insert, and then here's how we do that. Mongo client.connect, and then we pass that the URL. As is usual for long-running operations in the JavaScript world, and certainly in Node, this is going to be an asynchronous operation because it's going to go across the network. It's going to have to query the database. We don't want to be blocking our main event loop as we wait for things to come back. So the Mongo client.connect returns a promise. And that promise can be consumed by a .then. We could also use async await style programming here. But you see that I've got a .then and a .catch. The .catch is pretty easy. It's just going to report any kind of errors that take place as part of the connection process. So we'll look a little bit more at the then. As we saw in the Python client, the thing that came back from the connection was that database object. So again, I'm just using the convention that says, let's call this a DB. And then this interior of the then method is a fat arrow function that's going to get that connection object and then make use of it to do some inserts and queries and so forth. So print out a little connection message, and then I'm going to grab a collection. So db.collection, a little different again in terms of the interface that's provided, but it's going to get a collection called actors. It's then going to empty out that collection in case there was already an actors collection and it had data from a prior run just to kind of keep this clean. But you can see again, we've got methods defined on that collection class that we got back from the database. And then what we're going to do is just map over the actors that are listed in this constant list up here. So actors.map, and we're going to do an insert. So it's a map command, so it takes a function that's going to receive each of the actors in turn, which is just going to be one of these objects inside of the array. And then what it'll do is insert that one actor into the collection that we retrieved up here. So that would be the actors collection. And then because, again, this is asynchronous code, the interior here is going to have a then clause that will, first of all, run the find command inside of the body of the then with an empty selection list, which will give us back all of the actors that we inserted, and then iterate over those. For each of those, it's going to grab the actor and just log the actor details to the standard output. And then when that's complete, when that then resolves, it will hit the final then on the interior here and shut down the database connection. So output from this, as you might expect, I'm not printing out the details as they're inserted, as I did back here in the Python example. I'm only printing out the information in this log statement as the values are retrieved. So what we see is, well, that connection message, I guess I printed that up here, but then we see the specifics of each of those objects that were in documents that were inserted into the database with their automatically generated ID created by the node client in this case, and then the values that we inserted them using the static data up here at the top. So you can see kind of two different examples, two different languages interact with the database in quite a similar way. Some of the specifics of the function names and procedure calls and that kind of stuff differ from one to the other, but same basic ideas. Database containing collections, containing documents, very flexible in terms of adding and updating and inserting and removing and so forth. I can do that from any of the language drivers that are available.